Yeah. Good morning to all of you. Let's see, last time in this particular chapter, we have seen intensity, what is called as the magnitude. Thereafter, we have seen what are the different intensity scale is being used worldwide. Then we have seen this is the isosysmal map and how this isosysmal map is being drawn with various intensity levels. Then we have seen what are the different parameters through which the intensity is depends upon. Then we have taken several history of intensity scales. We have started with several intensity scale like Rossy-Forel scale, Mercalli scale, then the modified Mercalli scale, GMA, which is a Japanese meteorological agency, is also giving, you can see the intensity scale. So this all the scales we have seen. The detailed description you may find in the book of Kramer. You please, I suggest to refer this particular book for reading out this intensity, whatever we have discussed. Then we have seen what are the different levels of modified Mercalli intensity scale and how the damage observation is been linked with each of these intensity values. So we have, as we have said, the modified Mercalli scale is defining the intensity level, which is up to 1 to 12. 12 is the highest level, 1 is the minimum level. And each level is been actually linked with the observations, which has been described here. Based on the observation, you can link to the earthquake damages with each intensity level, and you can find out at a particular location what will be the intensity level it is been anticipated. Same way, we have also discussed what is the magnitude. So we have defined there are 4 types of magnitude scale. ML, which is known as local magnitude, which is being given by Richter. So this is, we have seen. Then the MS, which is the surface wave magnitude, body wave magnitude, and lastly, the seismic moment magnitude. We have started with last time ML magnitude, which is the Richter scale magnitude or a local magnitude. And we have defined with respect to how this local wave magnitude can be calculated with help of seismograph recording. So how to read those seismograph recording to find out the value of ML. As it has been said, it has been it has been given by Charles F. Richter. And he has actually converted various magnitude and distance observations and also the peak ground acceleration values into the equations. And he has suggested that this particular equation, he has actually suggested to find out the value of ML from the recording value. This is already we have seen last time. However, this particular method of finding out ML is having certain limitation, as this particular method is applicable to the particular type of seismograph instrument, which is being called as the Wood-Anderson type of seismograph. And it is only limited to this particular seismograph, and that is the limitation. It is the instrumental specific magnitude level, right? So local magnitude is the instrumental specific. So that is his limitation. It is only valid for South Californian earthquakes. As I said, it is only valid for specific type of seismometer. Has not been used by the professional seismologist in decades. And that is why it is much criticized today. Yes, please. Please.
Sir, PPT is not visible.
Okay. 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 Now? Now is it visible?
Yes, sir. Now. Yes, sir. Yes, sir.
Fine. So I have given the brief review of what we have done the last time. I hope you are aware. Okay. Now I'm going further for today's lecture, that we have already talked about ML last time, which is a Richter magnitude. Now we need to discuss this 3 magnitude scale, which is MS, MB, and MW today, right? So let's talk about a body wave magnitude first. For deep focus earthquake, reliable measurement of amplitude of surface wave is difficult. Amplitude of P wave are not strongly affected by focal depth. Gutenberg in 1945 developed a magnitude scale based on the amplitude of first few cycles of P wave, which is useful for measuring the size of deep earthquake. So as I said, it is the body wave magnitude, means definitely the recording of body waves, especially a P wave, is being used to find out the value of MB. So here they have used the value of P wave to find out the value of MB here. Second, very, very important, for the deep focus earthquake, the earthquake which has been occurred at very, very deep in the crust, right? So sometime such a very deep earthquake, the reliable estimation of the amplitude of surface wave is very difficult, because when it comes to the surface from the deep focus, then sometimes the value will be so less and it is very difficult to measure. In such situation, the seismograph, which measures the body wave magnitude or body wave amplitude, that has been employed to measure those values. Now, if you can measure this particular value of amplitude of the body wave, then the calculation of MB is very easy. They have given the one equation, that is log A to the base 10 minus log T to the base 10 plus 0.01 delta plus 5.9, where the value of A is nothing but the amplitude of the P wave in micrometers, that is number one. You can easily calculate from the value of seismographs or the time history. T is the period of P wave. So you can find out what is exactly the period or the duration of the P wave, right? So that is also you can find out from the history. And third is the distance of the seismograph from the epicenter. And that is in degrees that you need to put it. So once you put these values into this, you will get the value of MB. It's very easy, right? Similarly, there is a surface wave magnitude also. For example, suppose you want to measure the earthquake which has been happening. You want to measure the earthquake magnitude at the place it is very far away from the epicenter of an earthquake, right? For example, suppose the earthquake happens somewhere in Bhuj and you have the seismograph station which is at somewhere probably in Delhi, which is quite a far, almost 1050 kilometers away from the epicenter. In such situation, which particular seismograph will actually record those record this value, and which particular magnitude scale is being used? In such conditions, probably the surface wave magnitude will give us solutions. So the Richter's local magnitude does not distinguish between the different types of waves. As I said, it is the instrumental specific seismograph. So at a large distance from the epicenter, the ground motion is dominated by the surface wave. As I said, while we are discussing the characteristics of the surface wave, we have said the surface wave can travel horizontally to a large distances. And that is the characteristics we are using here to measure the surface wave magnitude of the scale. And with this particular principle, he has given Gutenberg and Richter in 1936, he has developed the magnitude scale based upon the amplitude of the Rayleigh waves, R waves. And he has given this equation, you can see, which is quite similar. MS is equal to log A to the base 10 plus 1.66 log delta to the base 10 plus 2, where A is the maximum ground displacement in micrometer, but this displacement or the amplitude you need to consider for the surface wave only, right? In the previous case, we have taken the amplitude of the body wave, which is a P wave. Here we are taking the amplitude of surface wave. In the ML scale, we have taken, irrespective of any waves, whatever the value of maximum amplitude we have taken in the case of ML, which is the Richter magnitude, what we have seen earlier, right? So that is what the basic difference in taking the amplitude in each three different magnitude scale, right? Delta is the distance of seismograph from the epicenter in degrees. So surface wave magnitude is used when the shallow earthquake is there. Earthquake which has been happening at a shallow depth between 10 kilometers to 70 kilometers depth. Probably you can use this surface wave magnitude by putting the equation in this. So if you see the scale of each magnitude, so here you can say this value where the P wave has been reached, where you are measuring the value of MB. If you want to measure the surface wave, you are actually, you need to see the recording somewhere here. So this is the surface wave recording. So here the whatever the value of maximum value, that is you are going to plot it for MB value, right? So this is the basic difference from where you are going to take the value of amplitude for the MB as well as for the AMS. Now, since you have seen 3 different types of magnitude scale, now if I put this magnitude scale on a same platform, then I need to see this where this particular magnitude scale is been saturating, right? So if you see here in this scale, the magnitude saturation is the general phenomenon for approximately the MB, which is a magnitude, body wave magnitude, is saturating at magnitude 6.2. Means beyond 6.2, it will give this flat values. You can see this is a line, which is a linear line, but after some point of time, it becomes a flatter. So you can see this magnitude is almost, you can see the 6.2. So beyond 6.2, the body wave magnitude cannot give this value. So at the same time, if you see the surface wave magnitude, so this saturation will come at the magnitude level of 8.3, right? From this graph, you can see this is a, you can see the in general graph, it has been plotted. So as MB is approaching to 6.2 or MS is approaching to 8.3, there is an abrupt change in the rate at which the frequency of occurrence is decreasing with the magnitude. Though the rupture area of the fault is large and the prediction will saturate at this magnitude, because of this magnitude saturation, the estimation of magnitude of large earthquake through MB and MS is become erroneous, right? So it is very difficult to measure the MB and MS if you use these scales for the large magnitude scale, because it saturates at certain level of magnitude durations. So this is the basic limitation is been addressed by the 4th magnitude scale, which has been commonly known as moment magnitude scale, and it is widely used in the world. So whenever I'm referring to the magnitude, it means it is a moment magnitude scale. So basically it has been said that all this magnitude scale to put on a common platform, you need to convert this MB, ML, MS, whatever the value of magnitude scale that you are using, that you need to convert to the moment magnitude scale. So let's see what is exactly the moment magnitude scale. So a really great earthquake at last minutes release the energy over the hundreds of kilometers. These are the several points of an earthquake energy release. Need to sum the energy for the entire record. So these are all this consideration has been taken while you are finding out the moment magnitude scales. Moment magnitude scale is based on the seismic moment and doesn't depend upon the ground shaking level. The previous, whatever the magnitude scale we have seen, it is based on the amplitude level. So you can find out from the time history. But this is based on the seismic moment or the energy release that is being generated during the earthquake. It is only magnitude scale efficient for any size of earthquake because the magnitude saturation does not affect the results. So this is the only magnitude scale you can actually use universally, right, to put on a common platform. So what are the factors which is going to depend on this particular magnitude scale? So if I see this is the fault, you can see this fault, this is a strike and this is the fault which has been there. So this is a before an earthquake, it is look like this. In a less than 1 second, when the earthquake happens, the displacement is going to occur in this way. So this is the strike slip fault which actually displaces in this particular direction in the occurrence of an earthquake. So you can see what different parameters that you can actually retrieve from this particular phenomena. So first you can find out what is the angle of strike, what is the angle of deep directions, what is the depth at which the earthquake happens, And the same way, you can find out what is exactly the deformation or the slip that has been taken place. And this parameter you are going to use in calculating the value of moment magnitude. Let's see how this moment magnitude has been calculated. An estimate of energy of an earthquake is called as the seismic moment, which is M0, typically given in the unit of Newton meter. The various factors which contributes to the amount of energy released by an earthquake. The first is the surface area. We have already seen what is exactly the surface area in meter square. So which is nothing but the fault length multiplied by fault depth during the earthquake. So this you are going to consider. Second is the displacement or the slip. This is the slip, that is what actually we have calculated. And the third factor is the strength of the rock. The strength of the rock we are going to measure in terms of the rigidity. So that is the mu value, the rigidity of the rock which is along the fault. As the rock is more rigid, you need to have a more force to displace this particular rock. And in such cases, for displacement of the rock while it is rupturing, you need more energy, and more energy will be proportional to the more bigger magnitude of an earthquake. So if I summarize these values, this M0 you can calculate from A, which is rupture length, multiplied by the slip or the displacement, multiplied by the rigidity or the strength of the rock. So if you put these values, then you will get, you can say, the seismic moment M0. Now, as you can say, this particular thing has been given for the this graph is given towards the depth and the strength of the rock under various level, like in an oceanic crust, how this values has been actually distributing, like along the depth, the strength has been increasing up to certain level, and then you can say it is decreasing if you go more depth, because you are approaching to the mantle, and more and more elastic behavior will actually find it out. If you have, you can say, the crust, the same way, this will increase, then there is a brittle ductile transition will comes into the picture, and then after it will increase up to certain level, and then it is decreasing, it is approaching to the higher temperature and towards the mantle surfaces. So this way you can actually find out this value. However, this is for just an explanation how the strength of the rock below the earth is there, and how you can estimate the rigidity of the rock. So the standard rigidity of the earth crust, you can consider that is 3 multiplied by 10⁻10 Newton per meter square. So that is mu value is been actually standardized. However, it is different below the different types of continents. So if you want to calculate the moment magnitude from the value of M0, which is my seismic moment, then you can use this particular equation. The moment magnitude scale is a way of representing the seismic moment of an earthquake with a simple logarithmic numerical scale. The scale is designed to dovetail with original Richter magnitude scale, which was designated for smaller earthquake. So once you calculate the value of M0, you put this value of M0 here, and you will get the value of MW, which is your moment magnitude, from this very simple equation. So this way you can calculate the value. So this is what the explanation. If you go towards the several literature, then you may find number of such equation for MW based on the value of this M0. M0 is the same what we have explained here. There is a strength of the rock into fault area into total slip, and you may find number of such equation like 2/3 log M0 minus 10.7, where M0 is the seismic moment in 9 centimeter, right? And you can actually find out this particular value. So this way you can calculate the value of moment magnitude with this particular condition. Now let us understand what is seismic energy. Once both the magnitude and the seismic moment are related to the amount of energy which has been radiating by an earthquake, the Gutenberg and Richter is developed the relation between magnitude and energy. So for a particular type of magnitude of an earthquake is generated, then generally what amount of energy is been actually releasing. So he has found out a linear relation, which is log ES is equal to 11.8 plus 1.5 into ms. I will just go through it, where the energy ES is in erg from the surface wave magnitude ms. ES is not a total intrinsic energy of an earthquake transfer from sources such as gravitational energy, or to sink such as a heat energy. It is only amount radiated from the earthquake as the seismic wave, which is ought to be a small fraction of an total energy transfer during the earthquake process. Now, just see, this graph is very, very important, which will give you a lot of insights how the earthquake energy releases for a particular amount, particular type of an earthquake. If you see, this is the axis which gives the magnitude level, and this is the energy release is been actually taking place during the different famous earthquake which has been happened in the past, and this is the amount of energy is been released in terms of equivalent kilogram of the explosive, right, which has been plotted. This graph has been actually taken from USGS public domain. You can see now very easily, sorry, you just see, if you see the earthquake of magnitude 2 or less, you can see more than 10 lakhs earthquake happens in a year worldwide, which is magnitude 2. So as you can see from this graph, as you are increasing the magnitude, the number of earthquake will reduces. So for the highest magnitude of earthquake you can find out, you can see it's very less, either is even it's less than 1. You can see this is a less than 1 to go beyond 9. Am I right? Okay. Now just see, so this is the magnitude increases. So as I said, as the magnitude is increasing, the number of earthquake will reduces. Same way, if you see the energy release, so let's say if you say a magnitude of 2, the energy release is 56 kilograms of the explosives, equivalent to 56 kilograms of an explosive. Just very simple. Now just see, if you say the magnitude of 3, this will be multiplied to, or this will comes to 1800. How much? How many times? So if you just see this ratio, it comes around 32 to 33 times. So if you take the ratio of 2, then it will come around 32 to 33 times. If you go from 3 to 4, 1800 comes to 56,000. Then from 4 to 5, the energy release will be 18 lakhs. Then go from 5 to 6, it will come to 5 crore 60 lakhs, and so on. This energy is been increasing tremendously as you are going one step higher in the magnitude. So if you just take the ratio of this for each, then each ratio from this to this, from this to this, from this to this, it will be around 32 to 33 times. So for each magnitude scale, the amount of energy released during an earthquake is almost a 32 times of an energy. So if you see, for a larger amount of an earthquake, or for the larger magnitude of the earthquake, the huge energy is to be released, and which is almost, you can say, the 1,000 or multiple times of energy released in respect to the lower magnitude of an earthquake. So this particular value, this particular, you can say, the will give you 3 basic things. At a lower magnitude, number of earthquakes is larger, energy release will be lower. As you are approaching to the higher magnitudes, the earthquake, number of earthquake will reduces, and at the same time, the energy will release in a multiple of 32 to 33. So that is what actually seen from this energy testing. So this the same way the frequency has been actually given for various amplitude scale with the number of years. In 1900, what will happen to the magnitude more than 7.5 and magnitude more than 8, just is a difference of 0.5. But if you see, in a 1900, only 4 magnitude of greater than 7.5 happens, sorry, greater than 8 happens, while if you just take, you can see the 0.5 value lower, then you will say the number is 10. Similarly, in 1905, you can see the value, this is only 4 earthquake happens, but here 14 earthquake of magnitude 7.5 happen. So you just lower the 0.5 of the magnitude, still the number of earthquake will become so large, almost 2 times, 2.5 times higher in number, right? So that is what the statistics shows. Now, This graph is the tabular representation of the same, like earthquake per year. One earthquake generally happens in the world, which is 8 or higher. Severity is quite high, 18, 7 to 7.9, which I will term as a major earthquakes. 120, 6 to 6.9, I will put it as a strong earthquake. 6200, I will take it as a light earthquake, and so on. You can say, I will put it in this way. This is a very small experiment. An earthquake causes an average of 2.5 meter strike deep displacement over the 80 kilometer long, 23 kilometer deep portion of a transform fault. Assume the rock along the fault had an average rupture length of 175 kPa. Estimate the seismic moment and the seismic moment magnitude of an earthquake. You can see here. So moment magnitude is nothing but the area of the rupture multiplied by the slip multiplied by the rigidity or the strength of the rock. Area is given. You can see the area is given here, 23 and 80 kilometers, right? And the earthquake was 2.5 meters like deep displacement. Displacement is given, means it is a slip is given. And also the rupture strength is also been given. So you put it in this form, in this equation, you put it in the common form, like in Newton per meter or the 9 per centimeter, you will get the value of M0 here. And then you use this simple equation, what we have seen earlier, and put the value of M0, you can easily calculate the value of MW. So this way, you can use this equation. Now, I will also touch upon several ground motion recording equipments. As you know, the seismograph is going to record the ground motions or the earthquakes. This is the typical seismograph I have shown in the figure, which generally records, you can see the earthquake. It consisting of, you can see the simple drum like this, which rotates at the uniform velocity. And there is a pen here. You can see there is a small pen is here. So it is continuously rotating. Once the earthquake comes, it will rotate in this way. So for each earthquake, it will actually records like this up to the certain durations. And you can find out, you can say, from this particular type of recording. So this is a common terminology. This is a horizontal seismograph. Same way, there is a vertical seismograph in which this drum is actually becomes vertical, and it will record the vertical component of the earthquake. The same way, if you put into the different direction in the horizontal direction, like it will actually measure the north-south as well as the east-west component in the same way, right? So the actual ground motion at a given location is derived from the instrumental recorded motion. The most commonly used instrument for engineering purpose are strong motion accelerogram or the accelerometer. This instrument record the acceleration time history of the ground motion at a site called as accelerogram. So whatever the recording that has been happened on this particular paper, which has been known as accelerogram. By the proper analysis of the recorded accelerogram to account for instrument distortions and the baseline corrections, the resulting corrected acceleration record can be used by engineers to obtain ground velocity and ground displacement by appropriate integrations. So once you know the acceleration, you can convert it into the velocity, or you can convert it into the displacement by means of rather integration or by means of the derivations. Right? Now, let's see the type of accelerometer which has been plotted here. Now you can see this is the electronic transducer. Now the several seismograph is been actually converted to now you can see there are type of seismographs or accelerometer. It has been plotted. You can see here there are several electronic type of accelerometer is there. So the transducer which produce the voltage output. So basically nowadays, whatever the previously, you know, the pen has been there and the pen is actually putting this, writing this value of, you can see this earthquake history. Nowadays it has been converted to the electronic transducers. So basically it is converting to the voltage, and that is also equipped with the servo control system. So it is used with the suspended mass with the displacement transducer. So you can see this is the mass has been put. with, it has been connected with, you can see the spring here. So some stiffness component, so that you can say when the earthquake happens, this will actually rotate. This particular vibration has been converted into the voltage, and this voltage has been actually located. Sometimes piezoelectronic material is also being used. So mass attached with the piezoelectronic material, which develops the electrical charges on the surface. As this piezoelectric material is there, so when it is been actually moving, it will convert this particular movement into the charges, and thereby it records the earthquake digitally onto the seismograph. Generally, accelerometer are placed in 3 orthogonal directions, as we have already seen this, to measure the acceleration in 3 different directions at a time. Sometimes geophone or sometimes the velocity transducers are also attached to the accelerometer to measure the seismic waves velocities, right? So basically, this type of, this is a recent seismograph which actually adopted this particular technology to measure the earthquake recordings. In the next lecture, we need to see this ground motion parameters, which is also very, very important. I will just give you a very brief. That is, the earthquake history can be described using amplitude, frequency, content, and the durations. Amplitude can be measured in terms of PGA, EPA, PGV, EPV, PGD, etc. Frequency content is also very important. So we will see the various frequency content parameter like Fourier spectra, power spectra, response spectra, etc. And same way, we will also see the durations in the next lecture. The duration of the earthquake history, how to measure, what are the different parameters. So I'm stopping here. If you have any questions, I'm very happy to answer. You can put in the chat box. Thank you very much.